Hi everybody, I'm Skip Alzheimer. Welcome to the AV Geeks Lunchtime streaming show where we watch old 16mm films. And that last film was a silent film from the Mogul Brothers collection about specialized lubrication. Now, I don't know what part one had. I was hoping that part one would show up when we were scanning more of those films, but part two was exciting. I appreciate that you guys can at least appreciate that the variety of different things I'm showing you. It's like it's all over the map, and it tickles my brain, my ADHD brain, to have things from all over. And so hopefully it's not too off-putting for you guys. But I know the one thing that you've all been asking for is more films about the metric system. So behind me on the Sintel, I have Learning About Metric Measure. Enjoy.
For his school project, Jim is preparing to construct the sun and the distance between. The sizes and distances are shown on this chart. The diameter of the Earth is about 8,000 miles. The diameter of the sun is about 864,000 miles. And the distance between them is about 93 million miles. Jim had planned to use a scale in which 1/8 inch represents 1,000 miles. But Jim has become so discouraged trying to convert distances like 93 million miles into the scale's 1/8 inch units that he's about ready to give up the whole project. Then Jim's father makes a suggestion. Instead of using a common ruler with its clumsy 1/8 inches, inches, and feet, why not use this meter stick that he uses in his engineering work? It too is a kind of measuring ruler. Jim's father also shows Jim where to find more information about the meter stick. Jim learns that the meter is the basic unit of length in a system of measurement called the metric system. The meter stick itself represents the length of 1 meter, which is about a yard. Since Jim has decided to do his measuring with the meter stick, he wants to make a model of it to learn how it works. So he cuts a strip of cardboard 1 meter in length. Jim labels the cardboard strip with the word meter, followed by its abbreviation, M. Jim notices that the meter stick is divided into several smaller units. There are very tiny units. There are larger, numbered units, and there are units that are still larger. How do the sizes of these various units compare? To find out, Jim counts the largest of the units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10. Because there are 10 of these larger units in a meter, we can think of each of them as 1/10 of a meter. The word we use for 1/10 of a meter is decimeter. After he has marked the cardboard strip into decimeters, Jim labels one of the units decimeter and writes its abbreviation DM. As we have seen, each decimeter is also divided into smaller units. The numerals labeling these units tell us that there are 10 of the smaller units in a decimeter. How many do you think there are in a meter? Since there are 10 of the smaller units in a decimeter, and there are 10 decimeters in a meter, there should be 10 times 10, or 100 of these smaller units in a meter. Jim counts them in groups of 10 to see. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Since there are 100 of these smaller units in a meter, each is 1/100th of a meter. The word for 1/100th of a meter is centimeter. Each centimeter on the meter stick has in turn been divided into still smaller units. How many of these smaller units do you think are in a centimeter? We have seen that there are 10 decimeters in a meter. We have also seen that there are 10 centimeters in a decimeter. This makes a pattern of 10 to 1. Using the pattern 10 to 1, we can predict that there should be 10 of these very small units in a centimeter. Count them and see. There are 10 in a centimeter. The pattern, 10 to 1, works. Jim divides one of the centimeters on the cardboard strip into 10 of the very small units. If a centimeter contains 10 of these very small units, how many does a decimeter contain? Since there are 10 centimeters in a decimeter, there should be 10 times 10, or 100 of these very small units in a decimeter. Let's count them in groups of 10 on the meter stick and see. 10, 20, 80, 90, 100. If there are 100 of these very small units in a decimeter, how many should there be in a whole meter? How many did we find are in a centimeter? 10. How many centimeters are there in a decimeter? 10. And how many decimeters are there in a meter? 10. Do you see that this makes a pattern of 10 times 10 times 10, or 1,000? Let's count the very small units in groups of 100. 100, 200, 800, 900, 1,000, or 1,000. Since each of these very small units is 1/1000th of a meter, each is called a millimeter, a word meaning 1/1000th of a meter. Jim now makes a chart that shows the relationship between the decimeters, centimeters, and millimeters on the meter stick. The chart shows that 1 meter is equivalent to 10 decimeters. 1 decimeter is equivalent to 10 centimeters. And 1 centimeter is equivalent to 10 millimeters. To put it another way, 1 meter is equivalent to 10 decimeters, or to 100 centimeters, or to 1,000 millimeters. Since he is using the meter stick to build his model of the Earth and the Sun, Jim has made a new scale in which 1 millimeter represents 1,000 miles. According to this new scale, the diameter of the model Earth is to be 8 millimeters, since the real Earth is about 8,000 miles in diameter. The diameter of the Sun is to be 864 millimeters. And the distance between the Earth and the Sun is to be 93,000 millimeters, or 93 meters. To help him find a sphere of the right size to represent the Earth, Jim sets the tips of his calipers so that they are 8 millimeters apart. After Jim has found a sphere of the right size to represent the Earth, he looks for the point on the meter stick that represents the size of the model Sun, which is to be 864 millimeters. Jim has found out that the measure, 864 millimeters, can also be thought of as 8 decimeters plus 6 centimeters plus 4 millimeters. Just as the number 864 can be thought of as 8 hundreds plus 6 tens plus 4 ones. This is because the metric system works just like our decimal system of numeration by which we write numbers. Jim now blows up the balloon that is to represent the 864,000-mile diameter of the sun. When he has finished, Jim checks the size of the balloon on the meter stick to make sure it is 864 millimeters in diameter. By comparison with the sun, the 8-millimeter Earth model, which represents the 8,000-mile diameter of the Earth, is very small indeed. Jim now drives a stake and fastens the Earth model to it.
It just ends. I don't know what happened. Oh no. It just ends. We have no idea how it's gonna end. Was the reason that we didn't adopt the metric system is because explaining it was so boring. I have some theories, but I mean, they could have made that so much more dramatic, dynamic, like comparing like the fastest land speed records, or take something that's like sports related, or something that's super exciting, and I don't know. Nope. It's a science experiment, or basically, it wasn't even a science experiment. It was creating a model of the solar system. So, oh well. All right. Speaking of space, let's see how space technology improves the heart pacemaker. Enjoy.
This is 3-1/2-year-old Jennifer Garaccio. Since July 1973, Jennifer has been using a unique rechargeable pacemaker to increase her heart rate from slow to near normal. She joins some 60,000 other Americans who have heart pacemakers implanted every year. Developed by Johns Hopkins University Applied Physics Laboratory, the pacemaker makes use of power cells originally used aboard satellites in space. It is half the thickness and 1/3 the volume of earlier models and can be painlessly recharged from outside the body for 20 years. This eliminates the need for surgery every 2 years to remove and replace batteries. Mrs. Kathleen Garaccio tells what the new device has meant to her daughter Jennifer.
It's meant a lot because since Jennifer's had the pacemaker, there's been a complete change in her. She's grown in size. She's acting very normal, where before she really couldn't play or keep up with the other children. It also means a great deal to us knowing that she doesn't have to be operated on every 2 years. And also the size of it, that it's small enough for her. The other pacemakers were quite large.
What the pacemaker does is send an electrical impulse to the heart, speeding up Jennifer's heartbeat from a slow rate of 40 to a normal 72 beats a minute. And normal she is. She does nearly everything a healthy youngster can do, and especially enjoys playing with her brothers, cousins, and friends.
Hey! Hey! I wanted to comment. What? the comment.
And by the number.
And you'll go in. It's over.
Her routine is different for only 90 minutes a week when she recharges the pacemaker batteries.
Pacemaker charger is very simple. It's convenient enough to carry. You can take it anywhere necessary to charge her. It's also very good if we were on a week's vacation, we wouldn't have to take it with us. If you miss a week, you can catch up on it, but there'd be no harm to Jennifer if we should not do it. That alarm means that the charging head is not meeting up. It lets us know that it's not charging. When it stops, the green light goes on, and that means that she's being charged. And when the whole charging period is finished, a blue light goes on and lets us know that it's the end of the charge. This means that she's charged for another week. We won't have to do it until next week.
We asked Mrs. Garaccio about the outlook for Jennifer's future.
The outlook for Jennifer's future is very good. The doctors say that she can live to be a ripe old age, and she could grow up to be anything she wants to be.
The basic concept for the long-life battery in Jennifer's pacemaker has been proven in over 10 years of space use. A good example of technology for space now being used to help people.
This has been an Aeronautics and Space report presented by NASA, the National Aeronautics and Space Administration.
Oh yeah, the NASA meatball logo. It's the big thing, the meatball. So that film is from that time period when electronics had to have wood, or at least wood grain. Very odd time. To kind of, I guess that was kind of related to televisions and like consoles of like stereos that had wood. More furniture-ish, but like, why would you have a pacemaker charger that had wood on it? Like, is it cheaper? It's just weird. Anyways, that was that of that time, and that's why like even the original Atari looks like it's wood. It's so strange. Anyways, finish eating. My assistant, Kayshawn, scanned this, and he was like, yeah. It was fascinating footage, but it's a little on the gross side. So here is The Housefly, 3rd edition. Enjoy.
To most of us, the housefly is little more than an annoying insect that buzzes around in the warmth and shelter of our homes. It bothers us especially when we find it in the kitchen, on dishes and food, but otherwise it seems simple and insignificant. Yet the housefly is amazingly complex, and it can be a deadly menace. A master of flight, the housefly is agile and fast, and very difficult to catch. When it flies, its wings beat more than 200 times every second. The up and down motion of the wings is controlled indirectly by flight muscles in the fly's midsection, or thorax. The thorax moves up and down a mere fraction of a millimeter. These tiny movements are transferred to the wings along a series of hinge-like joints and amplified several hundred times by the wings. The number of wing beats can be measured by the tone of the hum. The higher it sounds, the faster the wings are beating. During flight, the legs are held close to the body to decrease air resistance. The wings constantly change their angle of thrust. This wing motion lifts and propels the fly through the air. The fly's wings are translucent and well adapted for rapid flight. The efficiency of each wing is increased by bristles on the leading edge. Minute hairs on the wing surface probably contribute to efficient airflow over the wing. The row of hairs on the trailing edge of the wing enlarges the surface slightly. Behind each wing is a halter, a vestigial wing, that acts as a flight stabilizer. The halters relay information about the fly's position in flight. The delicate antennae sense the airstream during flight, enabling the fly to control its airspeed. The many-faceted compound eyes aid flight by providing the fly with a panoramic view of its surroundings. The fly also has 3 ocelli, simple eyes, that sense differences in light intensity. Rapid extension of its legs enables the fly to land on any available surface instantly. To land upside down, the fly first extends its forelegs upward to make contact, and then swings the rest of its body into place. But how does the fly stay upside down? If we look at the fly from below, through a pane of glass, we see on the tip of each foot, or tarsus, a pair of claws, which enable the fly to cling to rough surfaces, and a pair of tarsal pads for adhering to smooth surfaces. The tarsal pads are covered with many fine hairs, the ends of which hold a sticky fluid. When the fly removes its foot from the glass, the droplets remain. As we've seen, the housefly is well adapted for flight. It is also well adapted for feeding in ways that seem unusual to us. To find and recognize its food, the fly has scent and taste organs. The scent organs are on its antennae, which are covered with sensory hair and olfactory pits. We often see flies standing on their food. Flies not only can taste with their mouths, but with their feet as well. The tarsi of the front legs have taste organs. The fly's proboscis, or feeding organ, extends from the head when the fly finds food. The end of the proboscis expands into 2 lobes. Here we see the lobes from below. Each lobe contains a system of channels stiffened by thin braces. By means of the channels, liquid food like this drop of sugar solution can be quickly absorbed. Some solids, like this grain of sugar, must be dissolved first. The fly secretes saliva onto the food. The liquefied food can be sucked up, pumped by a special set of muscles in the head. Because the fly can liquefy many substances with its saliva, it can find nourishment almost everywhere. The housefly not only feeds on our food, but also on garbage. It also feeds on manure. Fly larvae help us by breaking these wastes down. However, disease germs from the wastes stick to the body of the adult fly. Because of this, the fly contributes to the spread of disease. The housefly and close relatives like the face fly spread disease to livestock. Fly-borne disease germs can easily infect the body through an open wound. Flies transmit germs of cholera, typhoid, dysentery, polio, and many other deadly diseases. Millions of microbes are excreted with the fly's feces. Using a microscope, we discover a variety of fungal spores and bacteria in the feces. Microbes also stick to the fly itself. In fact, it is covered with them. When a fly walks over a suitable culture medium, it leaves a trail of bacteria, which soon develop into colonies. Using time-lapse photography, we can watch the growth of a bacterial colony that develops in the trail of a fly. The adult housefly feeds on garbage and waste. So do its offspring, which begin life in their source of food. The housefly begins as an egg laid by an adult female. She probes for a suitable location for her eggs. The female extends her ovipositor like a telescope to deposit the eggs in a source of food for her young. She lays them under the surface to safeguard them from enemies and dehydration. The tip of the ovipositor carries sense organs, which enable the female to lay her eggs side by side and in the right place. She lays about 120 to 150 eggs in a single batch, and 4 to 5 batches during her short life. After about 24 hours, the fly larvae, called maggots, hatch from the eggs. A slit at one end of the eggshell eases hatching. Maggots have no legs. They crawl by using powerful muscles which contract and extend the body, by using hook-shaped mouthparts at the pointed anterior end, and with the assistance of spines on their bodies that give traction. The maggot has no eyes. On the blunt posterior end are 2 dark spots. The spots are breathing pores, or spiracles, that lead into a complex system of air tubes. Delicate hairs keep out dust and liquid. By keeping garbage near our homes, We offer the fly a most favorable environment for its offspring, virtually on our doorsteps. Depending on the availability of food and on temperature, after about 5 to 6 days and 2 molts, the mature maggots are ready to pupate, a major step in their transformation into adults. This process takes several hours, but is shown here in several seconds through time-lapse photography. The pupa case, which is formed by the hardening of the final larval skin, is a small barrel-shaped container. Inside the pupa case, the metamorphosis from maggot to fly occurs. Special photography enables us to see the fly's heartbeat inside the pupa case. When the metamorphosis is complete, the adult bursts the lid of the pupa case, aided by a balloon-like tilenum on its head. When this sac expands, the head swells to about twice its normal size. The tilenum acts like a bulldozer, pushing open a path to the surface. By alternating expansion and contraction of the tilenum, the fly can reach the surface. Its spindly legs are of little help in this process. Once on the surface, the fly immediately begins to groom itself. The tilenum disappears, withdrawn into the head, never to be used again. As is true of all insects, the behavior of the housefly is purely instinctive. The fly is taught nothing. Its every act is an innate mechanism. On the average, females will live about 4 to 5 weeks, males only 3 to 4. The adult pumps blood into its crumpled wings to expand them. Then the wings stiffen. The exoskeleton soon hardens and darkens. The fly is ready to take to the air.
I love Sean's comment. Why doesn't this film end abruptly? You guys are cracking me up. You're hilarious. So I just saw that James Caan has passed, and I thought that I had a film. It was kind of a preview for one of his movies, Thief, but then I realized it's To Catch a Thief, which is not James Caan. It's a TV show. So unfortunately, I don't have something. Sometimes I'm able to do tributes. Sometimes I can't. It just kind of depends on what I can find. But I do have behind me another film set up, and hopefully this will make up for the metric system film. I don't know. I have not seen this. This is very exciting. So this is Lab Safety Accident at Jefferson High. Enjoy.
Some kid had gotten hurt at Jefferson High School last week, and of all places, the chemistry lab. My partner, Bruno, and I were conducting the follow-up investigation. My name's Grumman, and I have to admit this is the first time I'd ever been called into a high school chem lab. But I have investigated my fair share of accidents, and one thing I've learned is that there's nothing accidental about them. Somebody goofed.
Let's go, Bruno. Lieutenant, can I talk to you for a second?
Hey, not now, Bruno. I'm busy.
Okay, you're the boss.
The office sent us up to see Mr. Petrie, the chemistry teacher. He had an open period, so I figured he had plenty of time to talk with us. Bruno may not have been the brightest guy in the department, but he was a good man to have around.
May I help you?
Morning. I'm Lieutenant Grumman. This is Sergeant Bruno. I think you know why we're here. The place looked real nice. It was all neat and orderly. Clean floors and uncluttered tabletops. The guy even had safety posters on the walls. Hard to imagine an accident happening here.
It's very rare. But you know, a chem lab can be a dangerous place. There are hazards everywhere.
You're kidding. Where?
Let me show you around.
Lieutenant, can I talk to you a second?
Not now, Bruno. I'm busy.
Still busy.
You see this?
Yeah.
Nitric acid. 1 drop can burn a hole through your skin. Hydrochloric acid. Breathe too much of the fumes, and you could end up with permanent lung damage. And in here we have white phosphorus. Handle this the wrong way, watch out. Sodium. Mix this with water, boom! Typical chem lab has hundreds of different chemicals in it. If you're not careful with them, use some the wrong way, mix two that shouldn't be mixed.
Yeah. I see what you mean. Mr. Petrie told us how each and every chemical in his lab had been completely and properly labeled and stored in the proper manner. Flammable and volatile liquids were placed in a special storage cupboard. Caustic materials were on the lowest shelves, less chance of their falling, but they were off the floor in order to avoid contact with water. Incompatible chemicals, those that should be separated, were in different storage areas. It may have been a high school chem lab, but I could see this wasn't kid stuff.
Then there are all the other dangers.
There's more?
Afraid so. Smell a chemical the wrong way, you could be out for the day. Drink out of a beaker, I don't care how clean it looks. You never know what could happen.
Oh.
Squeeze bottles. Squeeze them too hard, somebody might not like it.
Sorry.
Light a gas burner the wrong way, and it could be lights out. Hey, you got some matches?
Oh, no, sorry.
Rebecca, you got some matches?
Oh, no, I'm sorry.
Hey, you got some matches? Yeah. Here. Hey, thanks a lot. Yeah. Then there are spills. And slips. And falls.
This place is a death trap.
No, not at all. It's perfectly safe, as long as you pay attention and do things the right way. It's like I always tell my students, be alert and proceed with caution.
Makes sense.
While it's extremely unlikely, accidents can happen and people can get hurt. And they must take the proper precautions to see that they don't.
Like what?
Like coming to class prepared for lab work. That means tying back long hair so it doesn't get in the way. Rolling up long shirt sleeves for the same reason. Removing loose and dangling jewelry. Shoes are important. Students should never wear sandals or other open-toed shoes. Using a lab apron is always a good idea. It not only protects clothing, but the skin as well. Splash-proof goggles are an absolute must, especially during experiments involving caustic or corrosive chemicals. Here's a little demonstration I show my students. This balloon contains acetone, red dye, and hydrogen. The heads are styrofoam. One has a pair of safety goggles, the other does not. I'm going to simulate a small explosion, one you might encounter in a lab. If this were a kid, he'd probably be blind. This one, maybe some minor facial burns, but nothing compared to losing your sight.
This guy seemed to have his acids and bases covered, so I decided to interview a few of his students.
What do you want to talk to me for? I didn't do anything.
Oh, just a few questions, yeah. I understand you were doing some kind of experiment today.
That's right. I was making a preparation of hydrogen, which, as you know, calls for mossy zinc and sulfuric acid diluted to a 3-molar solution.
Yeah, that's what it calls for, all right. So tell me about it.
Well, let's see. First, I had to dilute the acid.
How'd you do that?
Very carefully. Acid should only be diluted by pouring them into water. Never water into acid.
Why is that?
It'll mix better that way, with less chance of it splashing in your face. I poured the acid slowly, stirring at the same time. Then I rinsed the stirring rod in water and placed it on the bench. You're not going to believe this, but once I saw a guy put a stirring rod in his mouth. A good rule in the lab is to put nothing in your mouth. You should never touch the chemicals with your hands either.
How do you know you were diluting sulfuric acid and not something else?
Mix-ups can happen. That's why everything we use is labeled. And then we check and double-check those labels before we use them. It's kind of like what Mr. Petrie's always telling us. Be alert and proceed with caution.
Yeah, I've heard that. I figured it was time to give the kid a quick test. So what would you have done had you spilled some of that?
Spilled acid can really be dangerous and should be cleaned up right away. The best thing to use is a sodium bicarbonate solution, which Mr. Petrie keeps handy whenever we're working with acids.
What if you spilled a base? Use the same stuff?
Heck no. If you spill a base, you should clean it up with a vinegar solution. That's an acid. You see how it works? If you spill an acid, you clean it up with a base. If you spill a base, you clean it up with an acid.
Okay. Now, I know you were careful and all, but let's just supposing that you had spilled some of that acid on your skin. What then?
Acids and alkalis will burn your skin. You gotta get it off fast, using plenty of running water. And if you should ever get some in your eyes, you should rinse them for 15 straight minutes.
I could see this kid wasn't going to fall for any cheap tricks. Anything else?
No, that's about it. The experiment went okay, and then I cleaned up, making sure to dump all the chemicals in the right containers. Never down the sink, unless Mr. Petrie tells us it's okay. And then I cleaned everything I used and put it back in its proper place.
Okay, kid, you can go.
That's it? I'm off the hook?
Yeah, you're clean.
Great.
It was time to move on to somebody else.
Lieutenant, can I talk to you for a second?
Not now, Bruno. I'm busy. I understand you were working with a gas burner today.
That's right.
Pretty dangerous, isn't it?
Well, it can be if you don't know what you're doing, but Mr. Petrie gave us complete instructions.
Go on.
Well, the first thing I did was to make sure that the burner hose was properly connected to the gas jet and not the compressed air outlet. Then I lit the match first, and then turned the burner on. You gotta remember to light the match first, otherwise gas could build up in the air. Then I made sure to throw the match into the right container and not the wastebasket.
What would you do if there were some volatile materials around, like alcohol or ether?
Well, I make sure there's none of that around before I light the burner.
Okay. So what happened next?
Well, let's see. I had to bend some glass tubing for an experiment I was doing. First, I cut the tubing to the right length. I did this by making a deep scratch in the glass with a file. Then I covered it with a towel and bent it away from me using my thumbs. I fire polished the rough ends. Then I heated the bend spot with the tip of the flame and bent it away from me. Then I set it down to cool.
How do you know when it's cool?
Well, you can't tell by looking at it. A good way to tell is to bring the back of the hand down just above it.
What'd you do with the tubing?
I was setting up an experiment, and I needed to run it into a rubber stopper.
Sounds like that could get tricky.
Yeah, it can be. What you have to do is lubricate it first. Glycerin is best. Then you use a towel to protect your hand and insert the tube slowly using a rotating motion. You gotta be real careful. The stuff breaks easy.
Then what?
I had to heat some chemicals in a test tube. As always, I made sure the open end of the tube was pointed away from me.
Why is that?
For safety. When chemicals are heated, they can boil over very quickly and shoot out, especially when they're in a test tube. So what you gotta do is keep the open end of the tube pointed away from you and anyone else. And you should move the flame along the length of the test tube, not just at the bottom.
The kid was sharp. I thought I'd find out just how sharp. Let's just say, for the sake of example, that you did something wrong and you wound up with a fire on your hands, an alcohol fire. What would you do, throw water on it?
No way. Water would only make that kind of fire spread.
Well, what would you do then? Come on, quick, you got a fire on your hands.
First, I tell everyone to move away. Then I grab the fire extinguisher.
You know how to use it?
Sure do. Mr. Petrie showed us how.
And what if someone's clothing caught on fire? Would you use the fire extinguisher?
Oh, no. A fire extinguisher should never be used on a person.
Then what would you do?
I'd smother it using the fire blanket.
Located where?
Right over there.
Okay, kid, you can go.
Thanks a lot. Hope I helped.
Yeah, sure. It was one dead end after another. The first case I couldn't figure. There was no evidence of carelessness or neglect or improper supervision. The accident just should not have happened. Okay, I give up. I just can't figure it. You and your students are doing everything right.
What are we doing right?
Everything. Your lab is clean and well organized. Your chemicals are properly labeled and stored. Your students know how to dress for lab work. They wear safety goggles and aprons. They know how to handle chemicals, how to use a gas burner, how to work with glass. They know what to do in emergency situations. I don't get it. How could there have been an accident here?
Accident? What accident?
The lab accident here at Jefferson High.
This isn't Jefferson High.
What'd you say?
I said this isn't Jefferson High.
Is that right, Bruno? This isn't Jefferson High?
It sure isn't, Lieutenant. That's what I've been trying to tell you.
Good talking to you.
Anytime, Lieutenant.
Come on, Bruno, let's go to Jefferson High.
Okay, boss.
Nice lab you got here.
Thanks.
Like I was saying, Bruno may not have been the brightest guy in the department, but he was a good man to have around. Don't go away now. There's a test coming up. No, you won't be graded. You might even have a little fun with it. Okay, here goes. All the questions are true and false, and they come from the film you've just seen. So grade yourself. Spills can cause accidents, and they should be cleaned up at the end of each period. The answer is false. Spills should be cleaned up immediately. You should smell a chemical by placing your nose directly above the test tube. That's false. You should never smell a chemical directly. It's okay to drink out of a beaker as long as it's clean. Again, the answer is false. You should never drink out of a beaker or other lab containers. Splash-proof safety goggles should be worn at all times. The answer is true, because you never know when an accident might happen. Long hair should be tied back, as it is more stylish that way. That's false. Long hair should be tied back to keep it out of the way. Lab aprons should be worn to protect clothing and skin. The answer is true. Acids should only be diluted by pouring them into water, never water into acid. The answer is true. If you spill an acid, it should be cleaned up with a base. Again, the answer is true. When lighting a burner, you should strike the match before you turn the burner on. The answer is true. The broken ends of glass rods should always be fire polished. Again, that's true. You can tell when a glass rod is cool by looking at it. The answer is false. A glass rod should be lubricated before it's inserted into a rubber stopper. The answer is true. When heating chemicals in a test tube, the open end of the tube should be pointed away from you and anyone else. Again, the answer is true. An alcohol fire should be put out with water. The answer is false. An alcohol fire should be put out with a CO2 fire extinguisher. Hope you did okay. See you around sometime.
That was awesome. But this isn't Jefferson High School. So just like yesterday when we were talking about school bus safety and all the transgressions that took place on the school bus that I was on in high school, there were also many transgressions that took place at my chemistry class. I took chemistry and advanced chemistry in high school. And oh my God, the things that were going on. And I didn't really participate in them. I was trying to warn people about the problems. And one of them was a lot of kids loved breaking thermometers in half and playing with the mercury in their hands. That's a big problem. That's not very smart. And I said so much. Another time, they would go, somebody who was like in charge of the lab, but he was like really the worst person to be in charge of the lab. He was a high school student. He brought out some sodium hydroxide and he was throwing pellets at people, which if you touched your eyes, you'd be like, ow, because it's alkali and it's a big problem. This was all because our chemistry professor was ancient. He was like in his 80s. Mr. Jeffrey. was his name. We call him Mr. Jeff. And dude had been teaching since the 50s or something like that. He was ancient guy, very kind soul, but the class took advantage of him a bunch, and it was very sad. Because he was kind of clueless. He couldn't, he didn't know that things were being thrown behind his back and all that stuff. And I'm sure at the end of the semester or the year, he said, wow, we don't have any more thermometers. What happened? Anyways, yeah, you're learning more about my high school and how problematic it was growing up in rural North Carolina in a rural high school in Stanley County. North Stanley High School. I somehow got out of there alive and with much of my self-esteem intact. Not everybody was so easily got through that. Anyways, thanks for tuning in today. Love showing you guys films. We'll be back again tomorrow. I think I will have a special guest who will join us, and we'll be talking about computers, computer films, and I will be showing a computer film that I might not be able to stream on YouTube. We're gonna see what happens. But everybody have a great rest of your day. If you like what you saw, hit the thumbs up button. You can buy us coffee at ko-fi.com/avgeeks. Hit thumbs up, like, subscribe, blah, blah, blah. Keep cool, everybody. And we will see you again soon. I should say the Rewind Devil is real and shows up occasionally in film cans. But I should also say, please rewind and love each other. Take care of yourself. It's kind of rough for some people out there. So take care. We will see you soon.